it's even, polynomial with even degree, for sure give you a maximum or minimum. What about odd degree? It's odd, it could be like this, or it could be like this. Now what? The general property for odd degree polynomial is what? One branch tends to go up forever, one branch tends to go down forever, right? So for sure, those graphs of the odd degree polynomial will eventually intersect the x-axis for sure. Doesn't matter where you draw the x-axis, you're going to intersect the x-axis for sure. Okay, because one branch keep going down forever, one going up forever. So what can you say about the odd degree polynomial? For sure, it will give you the x-intercept, right? Doesn't matter what. Polynomial with odd degree will give you the x-intercept. And if you know about the intersection right here, what we learned before, say if C is the intersection, then f of C is equal to 0. See? The intercept, learn with 0 and linear factor. X-intercept right here, x equal to C. So the 0, x equal to C is the 0, and the linear factor is, talk about zeros, x equal to C, and the factor is x minus C, right? And the x-intercept is C comma 0. Those three things always go together like that. Okay, that is a little bit more from our textbook. Just want to show you the use of the turning points and the property of polynomial. Okay, last item for this section, I will talk about a very important theorem. It's called the intermediate value theorem. Let me erase the board. Intermediate value theorem. Value theorem. So abbreviated by IVT, intermediate value theorem. Okay? And let me first of all explain the idea, the concept of this theorem, and then after this I'll give you the formal writing for the theorem. Pretty much the theorem says this. If you have a function f of x which is continuous on an interval, closed interval, a to b. And basically, if you say a function continuous on the interval a and b, means what? A, b right here, x. You guys are going to draw the graph with one curve without lifting the marker up, okay? F continuous on the interval ab, closed interval, okay? Because we want to take the first point and the initial point and the final point, the first point and the last point. Okay, and the second condition is this. Say if you plug in a into f of x, say you got f of a right here. F of a. Okay, plug a into the function, you got f of a. This is the point. And that point is above the x-axis. And then if you plug in the point x equal to b, you have another point. And if the second point is below the x-axis, this is f of b. So one point is above the x-axis, one point is below the x-axis, and since the function f of x is continuous, you gotta draw the graph of this function from a to b as a non-stop curve. The intermediate value theorem said it doesn't matter how you draw it. Eventually, the graph will intersect the x-axis at a point C. Moreover, that point C will be somewhere in between A and B. And I'm not saying that you're going to have exactly one C. You may have a couple points. The graph could be like this. Who knows? All right, you may have a couple of x-intercept, but at least one. Okay? So the idea of the intermediate value theorem says this. If you have a function f of x which is continuous on an interval ab, then for sure you have the x-intercept somewhere between a and b. You cannot have the instance of c outside of the interval. Say, what if you have an intercept c right here? You draw from a to b like this. You see what happened in here? That curve does not represent a function anymore because it fails the vertical line test. Alright? So the point C gotta be in between A and B. We have a C, and that C will be in between A and B somewhere. Alright. Similarly, the second case, what if you plug in A, you have the first point below the x-axis. This is f of A. And B right here, above the x-axis, f of B right here. And you connect from A to B, you still have the intersection. Alright? So in general, you have a continuous function on the interval, and if the first point and the second point is the opposite side of the x-axis, one point is below, one point is above, or above and below, then the theorem says that for sure you will have at least one x-intercept somewhere between A and B. And according to what we learned before, the x-intercept is equivalent to what? The zeros of the polynomial, and you can find the linear factor as well. Okay, so let me write down the theorem formally. F of x is continuous on, let f of x be a continuous function on a closed interval A to B. And now I want to include two cases. F of A is above, f of B is below, and the other way around. F of A is below and f of B is above the x-axis. I'm going to say it this way. If f of A times f of B is a negative number, and you see why it's going to cover both cases. The product of two factors equal a negative number. We have two cases. Either this one is positive times a negative number, or it could be a negative number times a positive number. Positive means the point is above the x-axis. F of B negative means it's below the x-axis. And the other way around, negative positive means what? F of A is below and f of B is above. So by writing that way, I'm covering both cases at once. If f of A times f of B is equal to negative number, then there exists a number C. Moreover, C gotta be in between A and B, so I'm gonna write this way. C is less than B and greater than A, such that f of C is equal to 0. And you know what we mean by f of C equal to 0? We plug in C into input, f of C equals 0, it means C is the 0 of the polynomial that we learned before. We're doing three things right here. X equal to C is a 0, or x minus C is a factor, a linear factor, or C comma 0 is an x-intercept. That's what we're looking for. Okay? And this is the meaning of intermediate value theorem. Okay? And there's another question that you may ask. What is it used for? The intermediate value theorem. There's a lot of use for it. Let me just show you a couple of things. Okay? One of the bigger things that we are learning about polynomial is to approximate the x-intercept, approximate the zeros. Okay? So, the intermediate value theorem at least is going to give you the approximation if we cannot find the exact zeros. Say, for example, I have this f of x equal to x cubed minus x squared plus 1. Okay? Let's try f of 1. F of 1 is what? 1 cubed minus 1 squared plus 1, which is equal to 1. Let's try, it means I plug next equal to 1, okay? F of negative 2. Negative 2 is what? Negative 2 cubed minus negative 2 squared plus 1. This is negative 8 plus 4 plus 1 equal to negative 3. You see what? When I plug 1 in, I got 1 out. Look in the graph. 1 in, 1 out. I have the point right here. 1 right here. 1 right here. Second point, when I plug negative 2 in, negative 1, negative 2 right here, I got negative 3 out. This is the second point. So you see, this polynomial function, of course, polynomial function is a continuous function, okay, on the entire domain. So it's continuous everywhere, okay? So we have 2 points. One is below the x-axis, one is above the x-axis. So I know for sure that the graph will intersect the x-axis somewhere between negative 2 and 1. Even though I don't know exactly where the intersection is going to be, but I know for sure there will be an intersection, okay? Not to worry, I'll know the zeros somewhere in there. And if somehow you can narrow down, squeeze in the interval, then you're going to have a better approximation of the zero. Okay. You can read the book for it. They give you a method of finding and narrowing down the interval. Finding zero is not the best method. Very slow, but it works. Okay. Let me see if I can talk more about this, or I can give you an example on this one. This is off the book, but it's going to help you to find better. Let's talk about the book's method first. All right. So I claim this, and let's use this example right here. The book said that the theorem, intermediate theorem, said this: we can have a zero somewhere between negative 2 and 1. Question is, can we have a better approximation of the zero, say smaller intervals? Okay. So our book's method going to do this. We make a table for you. X and f of x, right? Try to list out negative 2, negative 1.9, negative 1.8, all the way to 0.9 and 1, and they're going to plug in all the values for x and calculate the value. Say negative 2, you got a negative number, negative number, negative number, positive number. Eventually, you guys are going to see that the sign going to change somewhere. I'm not sure where it is, but say it changed since I'm just guessing, or I'm not sure. It's negative 1.5 is a negative number, and then negative 1.4 is a positive number. And you know what? Instead of having the zero somewhere between negative 2 to 1, now we know that the zero is somewhere between negative 1.5 to negative 1.4. And you see, the interval that we have is way smaller. And then we're going to repeat the same method. We're going to list all the values in here. Negative 1.5, negative 1.49, 1.48, all the way to negative 1.4. We plug them in again. We look for the sign. Whenever I change the sign, you know that there's a zero in between. Okay? We see that in the homework. That was a book method. And there's another way. There are many ways. When you get to count 1, we're going to learn more effective way to approximate the zero. There's another way. Instead of test all the points. Another way is what? We just test the middle point. Alright? Say a middle point right here, and you plug it in. If that point is below the x-axis, then you know what? The interval is going to be, intersection is going to be somewhere in here. If this is above, then the zero is on that interval. Okay? And then you keep going a half. Alright? Keep going a half. Then you're going to test less point. You get to the approximation faster. That was the idea. But that's extra. Yeah. And I'm pretty much done with section 2.2 about polynomial functions. Thank you for watching, guys.